Hello, everybody. So today we're going to look at one of the first techniques of integration, which is integration by substitution. Now, one of the things that you're going to notice is that when you learn about different techniques of integration, is that more often than not, many of the techniques of integration are based on rules of differentiation. And the substitution method is no different. So the substitution method is based on the chain rule for differentiation. So before we get into the integration by substitution, let's take a moment to review the chain rule for differentiation. So now, if you recall, the chain rule is a rule that's used to differentiate compositions of functions. And a composition of functions, if you remember, more or less, is just having a function inside of a function. And so the general rule for differentiating a composition of functions is that the derivative of a composition is going to be equal to the derivative of the outer function with respect to the inner function multiplied by the derivative of the inner function. So here we can write that as the derivative with respect to x of f of g of x being equal to f prime of g of x times g prime of x. Or if we write it a little bit simpler, letting u represent that inner function, we can write that as derivative of f of u being equal to f prime of u times u prime. So now a couple of examples. Our first example here, we have f of x equals x cubed minus 3 raised to the 7th power. So when we differentiate this, so the outer function we see is going to be the 7th power. The inner function is x cubed minus 3. So if we differentiate this, f prime of x, that would be equal to, we apply the power rule to the outer function. That gives us 7 times x cubed minus 3 raised to the 6th power. And then we multiply that by the derivative of the inner function. The derivative of x cubed minus 3 is simply 3x squared. And of course, we can simplify this, multiplying the 7 and the 3x squared together to get 21x squared times x cubed minus 3 raised to the 6th power. Second example, if we have the tangent cubed of x, g of x equals tangent cubed of x. Now here, once again, the outer function is the power, because remember, this is equivalent to saying the tangent of x raised to the 3rd power. So if we integrate this, if we differentiate this, g prime of x, we apply the power rule, once again, 3 times the tangent squared x, then we multiply that by the derivative of tangent, which is equal to the secant squared of x. All right, so that's the chain rule for differentiation, which hopefully by now you're all familiar with. It's not a problem. Now, if we write these in integral form, in other words, if you kind of say, what would this look like as an integral? What would it look like? Well, remember that the integral is the antiderivative, so we're kind of going backwards here. So for our first example, in the integral form, we could actually say, write this as the following. The integral of 21 x squared times x cubed minus 3 dx is equal to x cubed minus 3 raised to the 7th power plus c. Of course, when you integrate or anti-differentiate, you're looking at the general antiderivative. That's why we include the constant plus c. Likewise, with the second example, we take the integral of 3 times the tangent squared x times secant squared x dx. This would be equal to tangent cubed of x plus c. Now, had we not known what the derivatives of these were at the outset, you might be hard pressed to try to integrate a function, to try to integrate these functions standing alone. If you saw, for example, 3 tangent squared x secant squared of x, you might not know just off the top of your head that, oh, that's the derivative of tangent cubed of x. So how do we go about, how can we use integration to help us solve these types of, solve these types of integrals? So now, if we look at this, we can generalize this integral form in the following way. What you notice, if you notice, in both of those cases where we had that, we saw that the integral problem, or well, let's start with the chain rule. When we have the chain rule, what we typically saw was when we differentiate that, we differentiate a composite function. The derivative ends up also being a composite function multiplied by the derivative of the inner function. And we saw that in both cases. So in the general integral form, what we see is, if we take that in reverse, in terms of integrals, we have a composite function, the integral of a composite function, multiplied by the derivative of the inner function, and that being equal to a composite function plus the constant. So our objective here is going to be to use the observations about the derivatives of composite functions using the chain rule in order to integrate composite functions and also to be able to integrate other types of functions as well. All right, so let's look at what this is about. So now when we're looking for the candidates of functions or integrals that we can use a substitution method for, one of the first things that we look for is, of course, a composite function. Because what we're doing here, the substitution method, we can think of as using the chain rule in reverse. So what we want to look for is a composite function. But there's one more thing we want to look for as well. We want to look for a composite function that's multiplied by the derivative of the inner function. Because remember, when we take the chain rule, we differentiate the outer function and then multiply by the derivative of the inner function. So in integrating composite functions, we want a composite function, but we also need to have the derivative of that inner function to some extent as part of the integrand as well. So let's say we have this example of 5 times 5x minus 6 raised to the 8th power dx. All right, so in our substitution, the idea is that we want to rewrite the integral into a simpler form, something that looks better, that will be easy for us to evaluate. So we begin, in this case, we're going to let u equal 5x minus 6. Okay, so now what's the 5x minus 6? Notice that that's the inner function. And then, of course, if u is going to be 5x minus 6, if we differentiate both sides here, the derivative of u, du dx, would be equal to 5, or we could say 5 du equals 5 times dx. So now note here, in this substitution, we have u for 5x minus 6. That's our composite function. But then we have the derivative of that inner function, 5 dx, also as part of the problem. So then this integral, if we write this in terms of u, would be the integral of u to the 8th power, because that's this part here, times du. So now, of course, written that way, it's very simple to integrate. We can apply the power rule. So if we integrate that, that will be equal to u to the 9th over 9 plus c. and then bring it back in terms of x. So remember that u was equal to 5x minus 6. And so this will give us 5x minus 6 to the 9th power over 9 plus c. And now this problem, along with any other integral problem, can be checked via differentiation. If we were to differentiate this function, we would find that we end up right back at the original problem, 5 times 5x minus 6 raised to the 8th power. So notice that in this problem, in this integral, there is a base function, u. This is an error here, that's 5x minus 6. And in the integrand, we also see its derivative, which was 5 times dx. All right. And once again, that's what you're looking for if we want to make, ideally, if we want to make substitution work. So let's take a look at another example. So here we have negative 3 cosine squared of x times sine of x dx. All right, so here, u, we're going to let be the cosine of x. We'll stop for a second. Let's look at the integral itself. So now, first of all, remember, what do we look for? We look for a composite function and the derivative of the inner function of that to be part of the integrand. Do we see that here? Actually, we do. We have negative 3 cosine squared of x times sine of x. Cosine squared of x is a composite function. You got the outer function of squared, the inner function of cosine. But then the sine of x, well, we know that the sine of x, or the negative sine of x, I should say, is the derivative of the cosine function. All right, so here, what we see is that we have that instance. We have a composite function, and then we have the derivative of the inner part of the composite function as part of the problem. And so here, we start by letting u equal cosine of x, that inner function. The derivative du, of course, is negative sine of x. And so what do we see here? We've got, for the cosine squared of x, we know that's going to be our u squared. And then we have the negative part, and the sine of x, the negative and the sine of x basically combine to be du. All right, so the 3 is a constant. We'll bring that down. So when we write this in terms of u, this becomes 3 times u squared times du. All right, so now you may be wondering, where did the negative go? Well, remember, the negative here was part of the derivative of cosine. So it got sucked into the du. That's why we don't see that here. All right, so now we have it in terms of u. We integrate. Now the integral, or antiderivative, of 3u squared is going to be u cubed plus c. And then putting it back in terms of x, u is equal to cosine of x. So this will be equivalent to cosine cubed of x plus c. And we see the same thing happen here. In the integral, we have a base function, which is our inner function, cosine of x. And in the integrand, we also see its derivative, negative sine of x dx. So when we're looking at the substitution method, that's one of the first things that we're looking for. All right. Now, there are other functions that may not necessarily fulfill this entire requirement that we could still use the substitution method for. All right. But we're going to, and in the next video, the next part of this video, we're going to do several examples of integration by substitution, where we'll walk through each of the steps and look at how we can even expand well, look at how we can use the substitution method to even integrate functions for which don't even appear to be compositions from the outset. So we'll get into that into the next video.